So now we're going to look at the base SI units. There we go. So these are the units we'll be using in this class. These are actually all of the units that you need to know all the units in chemistry. What we mean by this is these 7 units make up every other unit you're going to learn in chemistry. So later on we'll talk about a concept called energy. It's actually a combination of these units. Now, for us, we will primarily be focused on these first 5 here. So there's a very good chance you've heard of mass before, and that's going to be measured in kilograms as its base unit. Everything is compared to the kilogram. Length, measured in meters, is also a unit I'm guessing you've heard before. Temperature, you may or may not have heard of the Kelvin scale. It is similar to the Celsius scale. It's just shifted over some. And we'll explain that more when we start using temperature in class. We also have time in seconds. That's not different between the English unit system and the SI unit system. Everybody uses seconds theirs. And then finally, this 5th one called a mole. We have a whole chapter about that coming up. So if you don't know what a mole is yet, you will by the time you get to the next chapter. So chapter 1, about half the chapter is about what is a mole. And then candelas and amps are units, but we're not going to be using them a lot in this course. In the second semester course, you will use amperes a little bit when you get towards electrochemistry. And we just won't work with candelas. You may use this a little bit in your physics class. But I do mention it so you know there are 7 total units. And every other unit we come up with can come by combining these units together. So in addition to these units, there are some conversion factors you're going to need to know. This is like our basic vocabulary so we can do things. I strongly encourage you're going to need to memorize these because you're going to use them so often. So you need to make sure you know what they are. So here are the ones we're going to have to memorize in total. So we have that 1,000 meters is 1 kilometer. I've also over here got it written as a fraction. These fractions will be helpful later because they're how we're going to do our conversion math. So you can memorize just these 2 things are equal to each other, but you'll see me use this by putting them in a fraction. I'll show you this when we get to the section in this chapter about conversion factors and how they work. But I'll just mention that these things are equivalent statements, where the fact that 1,000 meters equals 1 kilometer means that if I write it as a fraction, this is equal to 1. And as we learned in math class, you can always multiply things by 1. It doesn't change their value. This is how we're going to use this information to convert from one unit into another in just a moment. Then we also have the fact that a meter is 100 centimeters, a meter is 1,000 millimeters, a meter is 10 to the 6th micrometers, a meter is 10 to the 9th nanometers. And when you write them as fractions, you can also flip them. So the fact that 1 meter on top is the same as 1,000 millimeters on bottom, you can also write it like this with millimeters on top and meters on bottom. You can also replace the base unit with other units. So for example, 1,000 millimeters is 1 meter. It's also true with grams. 1,000 milligrams is also a gram. When you get to volume with liters, 1,000 milliliters is 1 liter. So once you memorize these as meters, you know them also as liters, joules, and grams as well, or any other unit we use where we want to attach these prefixes to them. Once you learn them once, they're the same for all the other conversions. We're going to learn some other conversions throughout the class, and you can do them in the same way. So you'll be able to use them as fractions to help you make conversions. The one additional one you're going to have to memorize other than the one here is the fact that a cubic centimeter is equal to 1 milliliter. We're going to use this a lot just because it's a very common unit of measurement. So if you memorize these are the main ones you're going to have to memorize for this chapter. I will also mention that in this class I'm going to minimize how often I ask you to memorize things. I don't think it's that useful in most cases because you'll learn them over time as you use them, and if you don't have it memorized, you can look it up. But these get used so often that it can be crippling not to have them memorized. And if you were to try to look this up each time, problems become unmanageable because you just have to keep looking for these things over and over again. So you really need to memorize these to help you do the questions we work on. Now, in addition to these units, there are some other ones you're not going to have to memorize. So this slide, I'm just going to show you that these are also units. You can refer back to this if you ever need to, but if you're using this on something like a test, I will tell you this conversion on the exam. So you may notice some of these are just ones you don't use a whole lot. Like we don't use a gigameter for much of anything. Now, you've probably heard of the prefix giga. For example, a gigabyte, which is a common unit of storage people talk about for hard disks nowadays. If you were older, you'd be more likely to be used to a megabyte hard drive, like the first gosh, I'm not that old. I'm like 35. I just turned 35. It's my birthday today. When I'm recording this, depending on when you're listening, it's not my birthday anymore. But 1 megameter is like 1 megabyte. And I remember my first hard drive was 40 megabytes, and I thought that was huge. I was like, wow, how am I ever going to fill this thing up? And now we have things on my phone that are bigger than that by themselves. So these things change. So these are a bunch of different units that we will use occasionally. You also have really small ones, things like picometers and femtometers. So for example, this can be useful if you're talking about what's the radius of a single nucleus, or an atom, or you're talking about a subatomic particle. This may come up. But we're not going to use them that commonly in this class. So if you have a problem, I'm going to tell you one of these things. It's also something that's reasonable to look up if you're doing a homework problem and you see something's in a megaliter. Not very likely, but if it comes up, you can look that up. And that's perfectly okay, and you'll be fine with that. Over time, if you end up, wherever science takes you, if you end up in a field where you use one of these a lot, for example, maybe you work with frequencies and you're going to use megahertz a lot, then you'll learn that a megahertz is 10 to the 6 hertz. So over time, you'll pick up the ones you need in the areas you learn. But if you learn those ones on the first page, you'll be good for this class. So now, we have one more concept to work in within these units, is something we call precision and accuracy. So accuracy is going to refer to how close a measured value is to its actual value. So for example, if I know that something weighs exactly 10 grams, it's a test weight, and I put it on a scale, and it says it weighs 9.9 grams, that's a more accurate measurement than if I'm told it weighs 9 grams when I know it actually weighs 10. Now, on the other hand, precision is a term that refers to how close together a series of measurements are to one another. So for example, if I weigh something 10 different times and the answers are very close together, it's precise. But if I use another scale and sometimes it's up a gram and sometimes it's down a gram, well, then that's not very precise. Oh, one other statement I want to make is when you first hear this, you might even think, well, don't I just care about accuracy? I just want to know how close I am to the right answer. In practical cases, when you're actually doing a measurement, you may not know exactly what the right answer is. So by knowing your precision, it helps to know how many times you need to make your measurement. For example, if you have a very precise instrument, that means I don't have to worry that, oh, if I measured it, it could be really far off. It's going to have whatever its accuracy range is with one measurement. But if it varies kind of wildly, I might need to measure 5 times so that when I average those together, I get an answer closer to a regular one. So taking this into account, let's look at this picture. Which target do you think there, A, B, C, or D, would be high precision but low accuracy? And I suggest you pause the video here and come up with an answer, and once you have an answer, then restart it. Okay, so with this, if I want high precision, I want things that are close together. So I look at my answers, those have to be A and B, because C and D are really spread out. But I'm thinking they're low accuracy, and I want to be in the middle of my bullseye, so B in this case is going to be my high precision but low accuracy example, whereas A would be high precision and high accuracy. You'll notice here that I have to have, whenever I talk about precision or accuracy, it's always going to be in comparison to something else, because in this case, A is very accurate compared to B. But if you were to compare it to a picture where you had I'm really bad at this, I'm not an artist, as you saw when I drew bread, if everything was exactly in one spot right in the middle, well, that's even more accurate than the spread out answer. So then my new one, poorly drawn as it is, might be more accurate than it was in A. So when we talk about precision accuracy, I would always ask you in the context compared to something else. Which of these two is more accurate? Because it doesn't mean something by itself. Now the reason this matters, so how does it play a role in lab? Where does it come up? Why am I teaching you about this thing when it comes to measurement? So let's have 4 students, and they measure an object with a known weight of exactly 100 grams. We have student 1, student 2, student 3, and student 4. If you look at their answers, student 1 looks like they're really close to the right answer. They're pretty close to 100 grams. Student 2 is a little high for his average, but some of his answers are really low. Like trial 2 is 86 grams, or trial 1 is 117, so his seems to vary a lot. Student 3 is really far off the right answer compared to student 2. He's actually less accurate, but his answers are really close together. And student 4 is similarly really close together but too high. So what does this mean? Student 2 has a large amount of what we call random error. What that means is his answers are going to be high and low, and it means if you pick any one answer, it's not going to necessarily be close to the right answer. They're going to vary a lot. They're not going to be very precise. This could be a student, maybe just they're learning how to use their scale, and so they're just not very careful with it, so when they put it on, maybe one time they lean on something, maybe one time they accidentally they put something on top of it otherwise, or they do something that makes it different, but it's not always the same thing. But student 3 has a systematic error where they're always too low. This means they're making a specific mistake where they're doing something that always makes it too low. Or their instrument has a mistake. Maybe their scale is calibrated incorrectly, so it's always reporting too low. whereas student 4 is a systematic error that is always too high. One thing to note about this from a practical perspective is student 3 and 4 have errors that are really problematic because when you're so close together, it makes you feel more trustworthy of your answer. You're like, this dude, I've probably got this right. I keep getting the same answer. I got to be good. So those systematic errors can be very difficult to find at times. And that's one thing that makes this work challenging is that you need to know what to look for. And this is why we have things like test weights. So that way student 3, if this was an experiment they were doing, they wouldn't realize they were off. But if I gave them a weight and I'm like, this is exactly 100 grams, they know, wait, I'm doing something wrong. I need to talk to Dr. Leslie. Maybe I need to try different scales. Something is wrong and I need to try to fix that. So this is why we worry about accuracy and precision, is that sometimes we're not very precise. We need a lot of measurements, then we're still kind of close once we average everything together, like if we're student 2. But if we're student 3 and 4, we need to know that just being precise, which is the part I can see if I'm doing an unknown where I don't know the weight, I might still be wrong and I need to pay attention to those things. And that's why we do things like calibrate, so we can find out if we're making an error like that.